You a cheapskate, Neil.
It's not my Zoom. Where did the Zoom come from, Craig?
It not uses the I don't know what's going on with it, but I told somebody.
Sorry?
Yeah, I think Jared booked this while he was in. I'm not sure. I'm not sure. Normally it works out. I'm not sure what happened. Yeah.
Never mind.
Hasn't happened before, but
We'll just wait. Maybe we'll just wait a few minutes for people to join. I'll just pass on to my group the address.
yeah, really interesting comments, Thomas, about defining marine heat waves, and yeah, this thing of like, I mean, where there's this image of the climate PDF moving in time. Exactly. Of course, on our planet, we only see one realization of that.
Yeah.
You know what I mean? So if you have an ensemble of climate models
exactly,
and they were perfect, that would give you the PDF, and you'd know, what percentile we're in as we move along. And I guess, which percentile you're in is really interesting from a dynamical point of view, like what's driving it specifically at this location. But, the hard fact about, it's 5 degrees warmer than anything we saw in 1980. That's a really important fact too.
Yeah. Absolutely. Also, if you look at the drivers, it depends how you define. As you said, define the heat waves. I mean, if you're only really interested in like what drives the peak change, or if it's actually the buildup of the heat, so that really depends on how you define these heat waves. And also sometimes if you use this shifting baseline, if you only have the observation, it's actually hard to define the anthropogenic trend in temperature. If you only have one time zero, it's actually really hard to come up with the shifting mean baseline, which really makes sense. There are many things which are a bit tricky actually for both the baselines, I think. Yes. Okay.
Right.
People are still joining, so maybe just one more minute, Thomas.
Okay.
If you mind. Yeah. Sorry about this.
No, it's good.
Nathan had a comment on the baseline definition. I don't know if he wants to jump in with voice.
Oh, yes.
I will, because I find it, if you think about it, really we're talking about the emergence of a new climate, right? And if you keep on shifting the baseline, you keep on sort of saying as a communication that the climate hasn't really changed, right? And at the heart of this, the impact is huge changes in the probability to the point that you have a new climate. And so I dislike shifting baselines for that reason. It's terrible messaging in the sense of how do you talk to the changing risk and then the emergence of a whole new climate. Planet's never seen it.
I fully agree. So, but the only issue is for example, if you take this hop day definition, which actually has a 90th percentile as its relative threshold, which is really low, like every 10th day is actually a extreme event. But then if you apply that definition, actually in the future, you get permanent heat wave conditions,
Yeah.
That also makes it then a bit difficult to communicate, because then everything is just extreme permanently, which I think it's fine. I am also fully supporting the fixed baseline approach, because we are interested in the total risk and it's better for the communication, but it makes the analysis also a bit tricky, if we go to really high warming levels,
Yeah, so the fractional attributable probability is well beyond 1, right? It's a new climate.
So it's just 1. Yes, one is the maximum. It's just it converges to 1, and that's the new climate. Yes.
All right, Ben. I think we might continue if that's all right with you, Thomas. Apologies for the break up here.
No, fine. Thanks. Yes. Okay, so we just had the question about this fixed versus shifting mean baseline. And actually, when we look what drives the changes in heat wave intensity, so is it actually the shift in is it the change in variability? So if the PDF actually widens or gets narrower versus the total change, and that's actually a figure from Clara Desert's paper from large ensemble simulations from all these different models. So if the ratio would be 1, that means the variability changes explains the total change in heat wave intensity. And you clearly can see that's basically, yeah, it's maximum of 10% globally, which actually the variability changes actually explains the total change. It's mostly the shift in the mean or the shift in the PDF towards the right, towards warmer temperature, which explains most of the changes. That's not really the case in the Arctic Ocean, where due to the change in sea ice, you also have changes in the seasonality of SST. Yes. And I think I just want to highlight one thing which also came up last week at the Liège colloquium on ocean extremes. I think when we look at the models, I think they are relatively good in representing the magnitude or intensity of heat waves. So these are kind of CMIP5 type models. But I think when it comes to the duration, they're really still lacking some basic features, I think. And now you could argue because they heavily overestimate the duration compared to the observations. Now you can guess, well, that's probably the resolution. But even if we go to really high resolution, that's a 10th to the degree CSM ocean model coupled to a high resolution atmospheric model, actually it still overestimates quite heavily the OESST based duration of marine heat waves. And that's the same for this GFDL high resolution 0.1 degree ocean model. So either actually the estimate from the satellite is somehow biased because there are also assumptions about how to fill the gaps when you have clouds and so on, or we are still lacking something in the models. Okay, so let's go to biogeochemical extremes. So when we look, and that has been done in collaboration with the group from Nikki Gruber at ETH. So we run a high resolution North Pacific regional model here over this area here on the Northeast Pacific. And we looked at the area affected by either heat waves here in light red, by heat wave and low oxygen extremes by orange, by heat wave high acidity extremes in purple, or triple compound extremes when all extremes actually happened at the same time and space. And you can see that especially during the blob period, actually, we didn't only have heat waves, we also have low oxygen extremes and high acidity extremes. And often we had these triple compound extremes. So probably, actually, the impacts we have seen during the blob were not only associated with the high temperatures, they were probably also associated with low oxygen and high acidity. So just to briefly introduce you the idea of compound events, which you might know even better than I do. So the definition is basically, it's a combination of multiple drivers or hazards that contribute to a societal or environmental risk. And there are different types of compound events. So there are preconditioned events. So for example, if the soil is already really wet and then you have a heavy precipitation event that leads to flooding, that's kind of preconditioned the system already. If we have a temporally compounding event, that means we have, for example, many heat waves, one after the other. Spatially compounding, we often have during El Nino phases where you have high temperatures in the Eastern Equatorial Pacific, but for example, also in the Northeast Pacific or in Northwest Pacific. And then we also have multivariate compound events when more than one driver is outside the norm simultaneously. So at the same time and the same space. And I mostly focus on them in the next slides. So when we look at hotspots of compound marine heat waves and high acidity events, so if the pH is really low or the hydrogen ion concentration is extremely high, at the same time as really high temperatures, where do these conditions actually occur in the global ocean? And that's mostly here in the mid latitudes and not really in the high latitudes where the likelihood of such compound events is really low. And also in the Eastern Equatorial Pacific, actually the likelihood is really low that compound marine heat waves and high acidity extremes actually occur. So that's based on observations, so that's not a model. But we also use then time series station data to look actually if the underlying data set, which has some assumptions, actually matches what we see at these different time series station data. And you see that actually in some areas, it actually matches very well. In other areas, there are some uncertainties. But I think the overall pattern is relatively robust, except, for example, in the Southern Ocean, where we do not really have a lot of PCO2 data. So, but what drives then this pattern? And we have in another paper, we just looked at the drivers of high acidity extremes. And that gives you, when we understand that, then also an explanation why we see that pattern here. And we also looked at, again, at the tendency terms for temperature, but also at the carbon tendency terms in the GFDL model, in the MOM5. So what drives actually DAC and temperature changes, and what drives then high acidity extremes? And I think you do not really need to understand all the different terms here, but what is shown here is that actually, especially in the mid-latitudes, it's also the air-sea heat exchange, so anomalous heat uptake in the mid-latitudes, which leads to higher temperatures. And because the carbon chemistry is sensitive to temperature, the equations, that leads to an increase in H+, especially in mid-latitudes. So basically, we have the same drivers, which leads to high acidity extremes, as well as to temperature extremes in the mid-latitudes. And that's also why actually in the mid-latitudes here, we often have these high acidity extremes and marine heat waves co-occurring at the same time and location, because they are often driven by the same physical process, basically less latent heat outflux from the ocean to the atmosphere and more shortwave radiation absorption, usually during these marine heat waves and high acidity extremes. That's not the case in the Eastern Equatorial Pacific. So high acidity extremes are often caused by more upwelling of carbon-rich deep water to the surface. But if that is the case, actually, we also bring more cold water to the surface. And therefore, it's really highly unlikely that in the Eastern Equatorial Pacific, we have at the same time high acidity extremes and high temperature extremes. Okay. And then when we look at the future changes in these compound events, again, they can be caused. So now we have a multivariate extreme, so one hazard and the other hazard. And if we have just a pure shift in the mean of one variable, that leads to a higher increase in compound event frequency, but we can also have a change in the variance, for example, in one driver, which changes then the compound event frequency. But because we have two hazards now, or two drivers, also the dependence or the correlation between these two drivers can change, which can lead then to a change in compound event frequency. So we have three kind of processes which can lead to a change in compound event frequency. And we have investigated that for heat wave and high acidity extremes. So basically here, that's the change due to the total change, basically due to the mean change, here in the middle due to the variance change, and here the change in compound event frequency due to the change in the dependence of the drivers. And what you can see here that, yeah, because high acidification has such a high signal to noise ratio, basically already at 0.2 degree global warming and an uptake of anthropogenic carbon, the whole surface ocean is actually in an extreme acidity state. And every time when we get a marine heat wave, basically we have a compound event, compound marine heat wave and high acidity event. But if we get rid of this mean change in the PDF and only look at the impact of change in variance, we also see a big change. And that's mainly caused because the acidity extremes are actually changing quite drastically. Even though we get rid of this mean change, actually the PDF widens quite heavily for acidity, which is not really the case for temperature. And then the dependence also changes a little bit, but I don't want to talk too much about that, but it also change a bit so that they get less correlated under a higher CO2 ocean, these two variables. And actually that leads to a little bit of decrease in the compound event frequency. But just to briefly mention, why do we have this increase in variance in acidity? So we looked at actually on which temporal scale does that increase in variance happen. So that's basically the latitude here on the x-axis. That's the change in variance in the future relative to today. And you see it's mostly the seasonal variability here, which explains the total change in variability in acidity. So why is that? We then decompose that into the different drivers. but in a nutshell, it's basically the seasonal variability strongly increases because the whole carbon chemistry, or the H plus, actually becomes more sensitive to SST variations in the future when the carbon concentration is higher in the ocean. So then for the same seasonal change in temperature, you get a bigger change in H plus variability, just because the mean background state in DAC, so in carbon, is higher in a future higher DAC ocean than today. So the sensitivity actually to the seasonal variations in temperature changes for acidity, and that leads to this large increase in variability, and then also to the large increase in compound event frequency, or to the sum of the increase, actually, what we see here in the middle. Yes. What we then also looked is actually what happens to the CO2 exchange, and that's just a paper we just submitted. What happens when we have a heat wave globally? What happens to the air sea CO2 exchange? And what we have seen is, so usually we have outgassing in the equatorial Pacific of carbon to the atmosphere. We have uptake in the mid-latitudes, and we have outgassing also in the Southern Ocean. And usually the whole pattern is actually reversed when we have a heat wave. So in the Eastern equatorial Pacific, we have less outgassing, so anomalous uptake. In the mid-latitudes, we have less uptake, so anomalous outgassing. And in the high latitudes, especially in the Southern Ocean, we have less outgassing, so more uptake. So when you do then a global average, actually the global average is near to zero, but locally these heat waves can have a large impact, but because there are some counterbalancing factors, actually globally the impact is almost zero. So I would expect for 2023, where we had almost global marine heat waves, that the impact on the air sea CO2 flux actually was globally minimal. That doesn't mean that locally it was not high, but if we average that, actually globally it was relatively minimal. And we also then looked at the drivers, and it's mostly driven by the PCO2 changes, which drives the changes in the air sea CO2 flux anomaly. Yeah, just another example about compound events. We also looked at compound marine heat waves and low primary production events. So that's the observation-based product or different products. Here we have two large ensemble simulations from GFDL and CSM. And you see that especially in the low latitudes, we have a higher compound event frequency of these marine heat wave low NPP events, relatively low compound event frequency in the high latitudes. But you also see that these models really actually differ quite drastically when we go away from the tropics towards the higher latitudes. You see that, for example, the GFDL has a really low compound event frequency, whereas the other model actually has a really high one. So that actually begs the question, are these models actually fit for purpose at the moment to really look at this compound event frequency in the higher latitudes? I think in the lower latitudes, I think they are doing relatively well. And we then looked at what drives actually these low NPP events during heat waves. So just to remind you, NPP is basically the growth rate times the biomass, and the growth rate depends on temperature, it depends on the light conditions, and it depends on the nutrients. So the more nutrients you have, the better the growth conditions. And we actually have looked at that then for the low latitudes, because the models actually show similar results there. So what happens is actually when we have a heat wave, we have a strong decrease in the small phytoplankton classes. So we have a relative shift during heat waves towards higher phytoplankton. So we have a shift in the community composition of these phytoplankton types towards more high phytoplankton classes. This may have then impacts for the export of carbon to the deep ocean, which we haven't really looked at yet. But what drives this decrease? It's mostly due to actually more nutrient limitations. So you limit the nutrient supply from the deep ocean to the surface during marine heat waves. That lowers the growth conditions, and at the same time, you also enhance the phytoplankton loss due to grazing, which is temperature dependent, and they usually like higher temperatures, so more grazing that leads to a decrease in biomass and therefore a decrease in net primary production. That's somehow compensated then by temperature, which actually boosts a little bit the growth of phytoplankton, but that's a smaller factor. So putting that all together, we have then looked how the ocean is actually experiencing these compound events in the future. We looked at the top 2,000 meter. We looked at marine heat waves, ocean acidity extremes, low oxygen extremes, and then these compound extremes. And actually, if it's gray, that means, for example, here in 1860, 40% or 80% of the ocean does not experience at any day actually extreme events, either in temperature, acidity, or oxygen. But if we use a fixed pre-industrial baseline, you see that actually at 2-degree global warming, over 95% of the top 200,000 meter of the ocean will face daily extreme or compound events under 2-degree global warming. So we really see that we go outside of the normal conditions the ocean is usually used to today when we actually go into the future. And even in the shifting mean baseline case, we actually have a small increase in these conditions, mainly because the ocean acidity extremes are strongly increasing with higher carbon conditions in the future, and the seasonality increases. So the ocean will face quite unprecedented actually conditions, I would say, in the future when we follow this, when we actually still increase the global warming and the anthropogenic carbon emissions, or we still do not actually reduce it to zero. And maybe just quickly before I end, I want to highlight just briefly some conflicting results we have about the impact of marine heat waves on fish and fisheries at the moment. So what we usually think about when we have a heat wave, and that's a paper we have published a few years ago, what happens to different fish species when a marine heat wave hits? What they usually do is, and we focused here on the Northeast Pacific, they usually lose biomass, they get smaller, the fish, they travel northward, and they also travel to the deeper depths to actually avoid the high temperature. So if it's reddish here, that it means that in these different large marine ecosystems, these fish species lost biomass, they actually moved northward, and they moved also deeper. And almost all these fish species we have investigated actually did that. And that's purely a model-based result. When we then look at the data, and actually colleagues did that, so Alexa Fredstone and Malin Pinsky did that in a recent paper, they analyzed actually sea bottom marine heat waves, and they also analyzed sea troll data, so basically more than 80,000 holes. They actually analyzed from a long-term survey in the North Atlantic, Pacific, and European continental shelf ecosystems, and they looked what happens to the biomass change from year to year, that's basically here on the y-axis, relative to marine heat wave cumulative intensity. Do we see any correlation between the marine heat wave intensity and the change in biomass? And it's basically, they didn't see anything. So what they concluded is, or what we concluded, marine heat waves were not associated with a decline in fish biomass, or the data is not yet there to actually make any firm conclusions about the impact of marine heat waves on marine fish. I think there are different hypotheses why that maybe is the case. So one could be that we may have to rethink the effect of marine heat waves on fish, or maybe we have neglected the role of compound events so far. Because we have done in a subsequent study, we coupled the model, the GFDL model, to a fish model, and then we looked at low fish biomass events. We identified them, and we went back what drove actually these low fish biomass events. We didn't look from a hazard perspective, we more looked from an impact perspective, and then looked back what were actually the conditions which led to these low fish biomass events. And what we found in that model, it was actually that it was mostly driven by low net primary production. So that's here on the right side. If it's green, that means that area of the ocean, the low fish biomass events were driven by low NPP events. And what I didn't show here is that actually compound events are a necessary condition for extreme low fish biomass over about 80% of the global ocean, at least in that model. So it's not only the heat which actually drives the fish biomass decline, It's mostly, at least in that model, NPP, and mostly also the combination of these driving factors, which leads then to low fish biomass events. Yes, so just to conclude, I hope I have shown you that marine heat waves, and as you probably already know, they strongly impact marine ecosystem, but they can also be important for the physical and socio-economic systems. They have doubled in frequency since the start of the satellite period, and they will strongly increase in intensity and duration in the future. Most of the impactful marine heat waves have a human-induced signal. And compound events, actually, when we talk about heat wave and ocean acidity extremes, they occur relatively frequently in the low to mid latitudes, while they are rare in the equatorial Pacific and the mid to high latitudes. And the blob was definitely a compound event. It was not just a univariate extreme event, it was a multivariate extreme event. And there are, at the moment, conflicting findings on the impact of marine heat waves on fish. And I think compound events, specifically marine heat wave and low NPP events, might have a greater effect than we probably previously have thought. Or actually, we do not really have the data at the moment to really investigate that, but that's probably something for future research. Okay, I think with that, I end here and I'm happy to take questions. Thanks.
All right, thanks very much, Thomas. That's an excellent talk. We'll open up for any questions people have. Craig, I can see one hand.
Yeah.
Maybe use an electronic hand if I can see you, Craig, but I might see some electronic hands also that are off my screen. Go for it, Craig. You ask first.
Okay, yeah, I was going to ask. So I'm an atmospheric scientist. Are these marine heat waves, I guess, from a climate within the climatology, is that often driven by low wind events, like just less surface stress on the ocean from the wind? Is that much of a factor, or is it more just how sunny it is? Yeah.
I think it depends where you are, but I think in the mid latitudes, that's often the case. So you have often blocking conditions, so high pressure conditions. Then you have usually also a little bit more shortwave radiation, and then often less wind stress, which actually reduces the evaporative cooling of the sea surface, which leads then to anomalous latent heat flux into the ocean. So yes, exactly. That's often the case, but I think it's not. I think it depends a little bit on the region, and I think you cannot make a global statement about that, but it's definitely in the mid latitudes, and the blob was definitely such a case. Yes. Yeah.
Thank you.
All right, I'm going to go in order of my hands that I can see on the screen. So the next one in line is Zijie Zhao.
Hello, Thomas. I'm Zijie. I'm working with Neil as a postdoc on the marine wave. Actually, your talk is very interesting and inspiration, and has a kind of a lot of inspiration. I'm kind of interested in your NPP results. I mean, the compound events between marine heat wave and low NPP. Can you move to the slides showing this?
This one?
Ah, yes, here.
Or
So
this
basically,
one?
actually, yeah, I think this one is fine. So actually, I think here you actually analyze the compound events between a marine, so actually between the co-occurrence of marine wave and the low NPP extreme events, but it's not always the case, right? I mean, in some regions, for example, so actually, for example, as what you can see here, in the equatorial regions, you can see there are actually a lot of compound events of marine waves and low NPP. But in the high latitude, I mean, for example, the high latitude regions, they don't have so many events. And in these regions, there is possibility that a kind of ocean temperature extreme, a high ocean temperature extremes can actually even enhance the NPP. So do you have any comments for that? Something.
That's absolutely right. That's a really good, exactly. So why is it actually blue here? That's because they do not often co-occur. So what happens when you have a heat wave, you often show the mixed layer, and you actually bring the nutrients closer to the surface. And actually also you have better light conditions as well. You have better temperature conditions for the phytoplankton. So all these conditions actually lead to more NPP usually during marine heat waves, you know, in the high latitude. So if you have a marine heat wave, usually the NPP is higher. And that's why actually the probability that low NPP events and marine heat waves actually occur is really low, you know, because usually heat boosts NPP to higher values, and then obviously you do not have a low NPP events, but they can still occur. So for example, so why do they occur? In the model, at least, that actually, so if you have really, during a heat wave, you have really high cloud conditions, then you reduce actually the light, at least in the model, that's the case, you reduce the light conditions so much that they do not have enough light to grow, and they still then, really rarely you get these compound NPP and marine heat wave events also in the high latitudes. But in general, that's really only rarely the case, and often we have a boost of NPP during the marine heat wave, yes.
Yeah, okay. So can I understand
no,
this
I think we better stop there. We've got a few other people who are on the queue, let's say. So if you can just hold that one, Zijay. Vanessa's next in line, please.
Hi, sorry about that. Mine might be quite long, so I'm happy to, if it's going to be too long, go at the end, because I was interested in the link between marine heat wave and the increased acidity in some areas, because on some sort of high level, I always thought colder water holds more CO2, usually more acidic. So I'm interested in what's the mechanism then when you get the higher temperature that actually you get more acidity then?
Yeah, that's basically just a pure thermodynamic effect. So this equilibrium constant for the different equations, they're actually temperature dependent. So if you actually increase the temperature, you basically shift the whole equilibrium towards more hydrogen ion concentration. So that's a pure thermodynamic effect. Yes. So usually what happens during heat waves, you lose actually carbon to the atmosphere everywhere. So during these high acidity extremes, during these marine heat waves, you actually lose the carbon to the atmosphere, at least in the mid latitudes, as I said before. But actually, that's just counterbalancing a little bit this temperature effect, but the temperature effect is still dominating in the mid latitudes. Yes. I hope that was right.
Okay. Right. So, Alex, you've dropped out. Did you want to ask your question?
I might ask quickly then. I just wanted to ask about the fish result. Yes. And what kind of fish were they? So you can imagine a situation where you get the local fish leaving, but a new cohort of fish coming in. Is that accounted for, or are these sort of benthic fish that don't move?
No, they're both actually, but they're both fish. But yeah, that's a good point. But they also looked at the composition of the fish species, if the composition has changed so much, but they also couldn't find a big change in, like, you have more tropical species or more like warm water species or so. They couldn't find that. But also, if you go then to the individual species, it's really hard, because then you do not really have a lot of data. So that's why they put everything into the same basket. Yeah. But no, they couldn't find any like shift in the distribution of the individual species either. Yes. Yeah.
Thanks.
Yeah.
Okay, thanks. Yushin?
Hi, Thomas. Thank you for your talk. I think I just got a quick question about the human activities influence on those most extreme summer heat wave on record. So I noticed that for the WA, Western Australia marine heat wave, you don't have the FAR value for the intensity from memory. Yeah, I'm just wondering why is that?
Can you say again which one?
Yeah, the top one, the Western Australia 2011 one. So there's no FAR value.
Yeah, very good question. So we actually didn't have any model which can reproduce the process, at least the CMIP type of models. They were not up to speed to be used for that analysis. So actually the models were actually not, they couldn't really reproduce the marine heat wave there, and that's why we excluded actually. So that's why you have a dash there, yes.
All right, yeah. That's fine, thank you.
Nathan.
Yeah, thanks, Neil. Thanks, Thomas. That was a great talk. I think of the Richard Mateer paper, which had aragonite outcropping in the Southern Ocean as a future risk. And then you sort of have the slightly counterintuitive result that marine heat waves and ocean acid extremes in the subtropics. But is there anything in the subtropics that actually cares about that increase in acidity? So is it a dangerous thing when you compound temperature and ocean acidity in the subtropics versus, say, something like in the Southern Hemisphere where aragonite would actually be exposed at the surface?
Yeah, so two things. I think here we actually look at H+ and not omega aragonite.
Yep.
And usually, so that's a bit different. So we look here at the surface, and also, yeah, we do not really look at omega aragonite, which would have a little bit of different drivers because omega aragonite is less temperature sensitive than H+. So you would actually have a little bit of different pattern here. I think, yes, I mean, for corals, acidity and heat is really important, you know. So actually, it's actually important to really know high acidity, marine heat wave extremes also in the mid, well, or at least in the low latitudes here, for example, over the Great Barrier Reef and so on. So I think there are different species also in the mid latitudes which are sensitive to the acidity level, and not only, I think, in the Southern Ocean, but yes. I mean, your point that actually the Southern Ocean is one of the regions which becomes first under saturation with respect to omega aragonite or so, that's well taken. But I think here we focus on H+ and not on omega aragonite per se. So that's a bit.
So there are thresholds which are relevant then for the mid-latitudes, corals being an example.
Yes, I'm not a pure biologist, but there are thresholds. I mean, the threshold of 1 for omega aragonite is well established because below 1, actually, these calcifying organisms start to dissolve. We know that very well, but there are also thresholds actually when, for example, omega aragonite in the low latitudes is up to 3 units. But even there, you have thresholds actually which are relevant, and if it goes, for example, below 3, some organisms will already be negatively impacted. Yes.
Okay. So there was an aragonite qualification there by Vanessa for Craig that in the chat. There are a couple of other points in the chat. One before I go to Jara's question, if I can.
Sorry, Neil, I just want to chime in quickly. We've just got the ECR session after this that we're eating into.
Yeah.
So maybe just one more question and then we can jump across to that separate session.
Okay. Yeah, no worries. Yeah, thank you. Yeah. So Shijian Hu asked the question, he hasn't got a microphone. Is it possible that marine heat waves can affect the travel of fishes and hence distribution of fish and fish catch, but not directly the fish mass?
Good question. I think, I mean, they are mobile. If they can escape the heat wave, yes, they can actually, so they can actually escape the heat wave, basically. So that would actually change the fish catch in a potential location and not really the biomass itself, because then the fish actually can escape. But yes, that's definitely
all right then. We might stop there.
Yes.
Sorry, Jara. I guess we were just honouring the speaker, giving the time, given that we had that interruption. So look, I just want to reiterate. Thanks very much, Thomas, for a marvellous presentation, as you always do.
Thank you.
And most